there, welcome back. Time for video number 5 in our series, right? In this particular one, we are working on kinematics equations. So we're getting a little bit away from graphing, although I'm going to use a lot of graphs in here. But we're getting a little bit away from just interpreting graphical issues to actually starting to now do this with more of a mathematical algebraic approach. But this particular video is really going to kind of show the connection between the two of them. So apologize a little bit in advance. There's going to be some algebraic kind of derivation in here, but it'll kind of show you the connection between the graphs and graphically interpreting motion, especially velocity and acceleration, and then where some of these equations come from. So in this particular one, you may want to have a calculator, though I'm not really doing a lot of calculations in this particular one. The next one, I'll be working on some more specific, like analyzing story problems. How do I plug and chug? So this is more about where did the equations come from. So again, in here, we're taking a look at story problems and actually taking, instead of just a graph, how do we turn this into some mathematical approaches? And again, we've got a series of equations that we're going to end up using to analyze these problems. A couple of the key things as we're sort of going into this is to make sure that you're actually reading, but carefully looking at variables, which ones are velocity, which one's times, which one's distance, key words that are in the problem. Units and signs, of course, are always going to be problems, but units can give you some really good hints as to what variable is being referred to. And again, I'm not really going to do a whole lot of the algebra versus calculus that's in this one. We're really going to just talk about the algebra part to it, so that'll work. Anyway. So with kinematics problems, these are where you're always getting these, guy with 3 watermelons rolls down a hill. If his velocity starts at 0 and his acceleration is this, how far does he go before he crashes the cart? These are these kinematics kind of story problems about moving. And there are a lot of times some very artificial kind of stories to them, but it's really about learning how to manipulate these variables. So you want to be paying attention to word clues, word hints that are in there, like how far is a distance, as opposed to how long is usually time, how far is usually distance, how fast, you're talking about velocities, it's acceleration, there's no particular word for that, I guess, but kind of being able to pay attention to those general pieces that's in there. So as you're solving these problems, you're going to be looking at your general equations and always writing your general equations to work from. This particular one, in this video, we're going to talk about kind of where do these equations kind of come from. And then again, when you're done, you're always going to be doing sig, figs, units, calculations. So that plugging and rearranging, your basic algebra skills really are going to get tested on here. So here's an example of one from the last chapter. You got a race car's velocity increases from 4 meters per second to 36 meters per second over 4 seconds. What's its average acceleration? So when you've got something like this and you're trying to, gotta get my pen going on here, sorry. When you've got something like a car, right, and here's your, your lovely car that's moving. It doesn't have to be a fancy sketch. It's going this direction, right? It starts at 4.0 meters per second. It's going to end at something like this, 36 meters per second. It's going in one particular direction. This is t equals 4.0 seconds. Again, when I'm saying sketch the problem and think about what you've got, don't have to be fancy, but learning to sketch the problem is kind of an important part of this. And we're trying to figure out acceleration, right? What is its average acceleration? Now, we're not doing instantaneous, just an average acceleration. So what do we have here? Well, it started at this, so that's our VI. It ended at this, that's our VF. Do we have an equation that matches this? Well, yeah, and it turns out that we do, right? We have this particular equation, delta V over delta T equals A, right? Acceleration is the change in velocity over time. So again, with doing these, they're not necessarily challenging problems. It's just learning to slow down, picture the system, and figure out what we've got. Delta V, how do we do that? VF minus VI over delta T equals A. What are our parts? Well, VF is 36. VI is 4.0, right? VF minus VI over our change in time, which is 4.0 seconds. And then we get acceleration from that. So 36, I'll get my calculator going. 36 minus 4 is 32. Divided by 4 is 8. So this is 32 over 4 is acceleration, and acceleration equals 8. Don't forget your sig figs in units. How do we approach that here? We'll look again at your original problem. Almost always we're doing multiplication and division, so your least number of sig figs. We've got 2 sig figs here, 2 sig figs here, and 2 sig figs here. So our answer shouldn't be 8, it should be 8.0. So acceleration should be 8.0. And then Units is the key part to this. What are the units? Well, if you don't know what they are, you can look at the problem. This is meters per second, and this is meters per second. This is in seconds. Don't forget to look at that, because make sure it's not meters per second and then over 4 minutes, right? Something like that. Look closely to make sure that your units are consistent. So meters per second divided by seconds is meters per second squared. And that gives you the final unit that you've got. So again, doesn't necessarily have to be hard, but do make sure that you're paying attention to those pieces. Okay. When we have these, this was the equation that we just used, was that one right there, that acceleration doesn't change in velocity over change in time. I'll remind you that we do have a simple equation from our last unit, which is the velocity is distance divided by time only, and this is important, if no acceleration. This is kind of a key point. This equation right here only works in constant velocity. It does not work if the acceleration is changing. All of the other equations about acceleration. So you can see now we have 1, 2, 3 additional equations that we're going to use, and these are called our kinematics equations that are derived from these original two. So we've got to take a look at kind of where these are coming from. So these 3 derived equations, again, be happy you're doing distance learning. You don't have to necessarily memorize these. If you're not doing distance learning, if you're in person, you got to memorize these. I'm going to ask you these on the test. So how do we get to these? So let's take a look at some graphical analysis here. So we're going to kind of take a little bit of a pause here. If we have an equation like this, where there's no acceleration, we have constant velocity. It's going at 5 meters per second, and it's still going 5 meters per second. An important connection to calculus here actually becomes the idea of the area under the graph becomes important. We've talked about slope quite a lot, that the slope of a distance time graph gives you velocity. But what about the area under a velocity time graph? What the hell does that mean? It turns out that when you're trying to find displacement is the area under a velocity time graph. You're like, Bedwell, I thought you were telling me about equations. Why are you doing this here? They do connect back together, I promise. Let me make this walk back around. Okay, so how do I know this is area? What's the equation for area? Area equals, right, length times width, right? Well, what do we have here? Here is my area that I'm looking for. Imagine that this is the area under this graph. Well, what exactly is that? Well, length times width in this case is velocity times time. V times t equals what? Okay, it's the area of this. Take a look at our equation right here, right? Velocity is displacement divided by time. So let's rearrange this. Velocity times time gives you displacement. This is an area right there. That means that if I have a VT graph, the area under my graph of this rectangle right here is displacement. Hey, perfect. This is delta D right here. Again, I know that's a way easier to do it mathematically, but let's build on this idea. What if we are accelerating? Because remember I said this equation only works in acceleration. Well, what happens if we actually have a case where we're accelerating? So now if we're saying under the VT graph is going to be displacement, now we're not talking about a square, we're talking about a triangle, right? I know you guys know the area of a triangle, 1/2 base times height, right? That's the area of a triangle. Well, what do we have going on here now? Again, it's a little bit different because we've got acceleration. So we've got 1/2 of velocity times time will give us area. So wait a minute, let's take a look at this right here. We've got something else that we can kind of add into this. What if we don't know its velocity? What if we know its acceleration instead? So we can kind of do this. I'm going to take this little guy right here. I took my equation, acceleration is change in velocity over time. I rearranged it so that I have change in velocity all by itself. I'm going to plug this into here, right into that spot. So we get 1/2 a times time, or a delta t, times t again. Again, I plug this into where this velocity is. There's another time here. So this is 1/2 a t squared. This becomes an important way of looking at area underneath this. We'll see this as it comes up again in another equation. So we can say that this particular area underneath here could be represented 2 ways. 1/2 velocity times time works, or 1/2 acceleration times time squared. Both of these would represent displacement. Okay, I don't mean times each other. 2 different ways. One's using velocity, one's using acceleration. This one ends up being important for us. Okay, kind of step number 3. What if we have this, where we have a VI and a VF? This last one, VI was 0 and we had a VF to it. But what if we've got an initial velocity, it's starting at 10 meters per second and ending at 20 meters per second? What's the area under this graph? Okay, so if you take a look at this, this is kind of some 2 parts going on here. We have down here a rectangle, and up here we have our triangle. Well, this is 1/2 AT squared, right? That's what this particular one is, area under a triangle. This one under here is the area of a displacement. It's velocity times time. But take a look at which velocity it is. This is VI times t, not VF, right? VI times t. So if we start doing some interesting things as we start to pull these together, it's the sum of these 2 things. Displacement is now equal to VI delta t, how much time was there, and times its initial velocity, plus 1/2 a times delta t squared. If we know its acceleration. And we can also do, we can do the change in velocity over here as well. It's the same, or 1/2 delta VT also works. Oops, VT right here works as well. So again, we have some different ways that we can address this. Now, this looks like one of our kinematics equations. That's where this comes from. So when you see this crazy kinematics equation, do I have it on the next one or not? Hold on, do I have it on the next one? I don't think I do. There is the very original one. Hold on, going back. There it is, right there. See it right here? This is one of our kinematics equations. This kinematics equation is literally just a rearrangement of acceleration is velocity divided by time. This equation right here and this equation right here are the same thing. This equation right here is the area equation. Area under a velocity time graph is actually what we're doing in this crazy long equation. So when you look at this, like, why is this so crazy long and hard to remember? It's just area under a VT graph is all it is. But it's area under a VT graph when we've got some initial velocity to it. So that's really all it is. By the way, there's a DO that's in there just in case you're starting at some, a head start or something like that, in case you have an initial position. Okay, so in terms of this, by the way, if we're doing calculus versus algebra, we've talked a little bit about this. What happens if we have slope here, right? We know that this slope is acceleration, and we know that the area underneath this one is displacement. These are important concepts for us, that when we're talking about algebra, when we're looking at these, that the slope of one of these lines is equal to acceleration. The area underneath there is called displacement. Hey, super easy when it's linear, but what if our acceleration is not constant and it's doing one of these kinds of things? If our acceleration is changing and we have a curve, that's when we have to use calculus. And by the way, these relationships are the same. It's just a little bit of a different kind of a math approach. In trying to take the slope of a curve, in calculus, we call that a derivative. And if we're trying to take the area under a curve, we can't use triangles and rectangles, we call that an integral. That's really all that it is. So if we have a VT graph, the slope of a VT graph is acceleration. The slope of a VT curve, or the derivative of a VT curve, the first derivative of velocity, is acceleration. If we're talking about the area under the graph, the area under a consistent VT graph is called displacement. The first integral of velocity is also known as displacement if it's changing. So again, if you're not taking calculus, don't worry about it. I just wanted to make that connection, that when we're kind of going up a level from displacement to velocity, we're taking a derivative. We're talking from velocity to acceleration, that's a derivative. They kind of depend on one another. When you're taking the area underneath it, we're kind of going down a level, and we call that integration or integrals. So just as an FYI. Okay, and then the last thing. I'm going to do this one very briefly for us. There are lots of cases in our velocity time graphs or our velocity VT graphs. What if we don't have time? Nobody got time for that. It's an old meme. Trust me, it's crusty. But anyway, if we have an equation like this one, and this was the one we just used in our last equation, where we've got an initial displacement, our initial velocity and time, we've got 1/2 AT squared. Almost all of these have time in them. There is an algebra solution that does not include time. Basically, this is it kind of described sort of right in here, where you take your equations for acceleration, you plug it in, do some plug and chug and rearrangement. We have a third equation right here. What's nice about this third kinematics equation right here, notice how there is no time present in this one. So this is VF squared, final velocity squared equals the initial velocity squared, plus 2 times the acceleration times the change in displacement. So again, this one is the nice one that we have if we do not have, don't have time. Again, I don't need to do the whole algebra for you. You don't really care anyway, neither do I. I can do it for you, but you don't really want. So we're kind of circling back around. As we do this, when we're doing kinematics, when we are solving story problems with algebra, rather than doing the graphical approach, although these are derived directly from the graphs, we can use these 3 kinematics equations. And you can kind of talk about these as being kind of starter equations if you want to, but here are our 3 major kinematics equations. Final velocity equals initial velocity plus acceleration times time, which is directly an algebraic rearrangement of this equation right here. We can talk about displacements if we know what initial velocity is and time is. This one does not have final velocity in it, but it does give us initial velocity and tells us what the total displacement is. This one down here has initial and final velocities, but it doesn't have time. So each one of these equations has a slightly different set of variables to it, so a slightly different set of uses. It depends on which one you want to use, depending on what you know in the problem, what you don't know in the problem. And that is what we'll do in the next video. See you there. Get your calculator ready.